Hi everyone, this is Scotty Johnson, and I did my research project on the fossil record and the evolutionary history, purpose, and origin of the turtle shell. To begin with, I just wanted to go over the anatomical structures of the turtle shell. So in figure A, we have the dorsal shell, also known as the carapace, and figure B is the ventral shell, also known as the plastron. And some important structures to keep in mind are the peripheral bones, costals, neural plates, and deep to these are the vertebra and dorsal ribs. Turtles are of the order Testudines, and they've been evolving for the last 280 million years now. And the origin and evolution of the turtle shell has actually puzzled evolutionary developmental biologists for many years, just since there was a lack of transitional fossils. And many hypotheses arose between various groups of scientists because of this, namely paleontologists and evolutionary developmental biologists. The debate consisted of the composite hypothesis, which basically states that the shell was formed by the acquisition of overlying osteoderms. This is very similar to the quote unquote armor that crocodiles and alligators have, or if the shell was formed not only from the acquisition of more and more osteoderms, but rather by the broadening of the ribs and vertebrae themselves, which was the de novo hypothesis. And paleontologists trusted in the composite model, but this hypothesis would be hindered by a substantial morphological gap within the fossil record. And the evolutionary developmental biologists supported the de novo model, and this was due to the fact that there was a lack in transitional fossils that would support the idea of rapid evolution of the shell. And so this would all change through the stem turtle Odonochelys semitestacea. And the discovery of the stem turtle Odonochelys helped support the de novo model of the origination of the shell. And from the fossil record, paleontologists discovered that Odonochelys had a fully developed plastron or ventral shell and only had a partially developed carapace or the dorsal shell. And it also lacked osteoderms and had distinctively broadened ribs and vertebra. So, with this new knowledge, Odonochelys proved that the shell didn't come from the overlying of osteoderms, and thus falsifying the composite hypothesis. Transitional fossils have shed new light and have provided scientists with evidence to fill the missing gaps on the phylogenetic tree. And in both of these figures, these fossils of stem turtles have provided the information we need to understand the evolutionary history and origin of the turtle shell. And so turtles are amniotes, which come from the clade of tetrapod vertebrates, and many of its ancestors have shown modifications, starting with one called Milleretta rubigii. Now, Milleretta was a basal amniote and has been identified as the first stem turtle, which existed over 280 million years ago. And the fossil record shows that Milleretta had 18 broadened dorsal ribs that were L-shaped in cross-section, and these ribs would present a transitional state between broad-shaped ribs that were discovered in later stem turtles and a rod-like structure found in stem amniotes. And eventually this would become an important morphological feature as other transitional fossils would arise. The next stem turtle has been identified as Unitosaurus africanus, which existed 260 million years ago and was a late Guadalupian Permian reptile. And so the unearthing of this transitional fossil was actually a major discovery, which ended up helping bridge the morphological gap between turtles and other reptiles. And so the major differences between Unitosaurus and Milleretta was the excessive elongation of the dorsal vertebra, which ended up exceeding 4 times its width. Also, there was a reduction of the broadened dorsal ribs and vertebra from 18 pairs down to 9, which interestingly enough would be morphologically consistent with extant turtles and is a quite unique synapomorphy shared between the two. Another feature was the modification of the ribs from an L shape in cross section to T-shaped ribs, which would be bowed in shape from the cranial view. Also, with Unitosaurus, another structure of bones would begin to develop on the ventral surface, but wouldn't be until another 20 million years with the next stem turtle that would actually aggregate together. This intermediate stem turtle is called Papacheles rosiniae, and it dates back to 240 million years ago during the Middle Triassic period. And Papacheles had some minor modifications in the ribs, but most of its anatomical structures remain the same, except for one major modification. And this modification is a structure of bones called the gastralia, which is a breast-like shield of bones, which is located on the ventral side between the pelvis and sternum. And this structure is actually very common in many other reptiles today. This structure is also very important just because it was the precursor to what would become the plastron, and it wouldn't be until another 20 million years that the plastron would become fully developed and functional. Odontocheles semitestacea is the next stem turtle, which lived 220 million years ago during the late Triassic period, and this would become the most primitive true turtle. Odontocheles had 5 pairs of gastralia, which eventually fused together to form the newly innovated plastron. With that, it also contained a fully developed plastron and a partially developed carapace. And with the partially developed carapace, scientists were able to identify the ossification of early neural plates, as well as the broadening and flattening of the dorsal ribs. And so, 10 million years after Odontocheles, signs of the fully developed shell suggested that rapid evolution had occurred. Next is Proganochelys quinstedii, which lived during the late Triassic period, around 210 million years ago, and it was thought that this stem turtle was the result of rapid evolution. And basically, this was because of the acquisition of the peripheral bones that formed a perimeter around the costals. Another modification was the reduction of the plastron bones from 5 bones down to 4. Since Proganochelys, few modifications have occurred, and this is Chelydra serpentina, which is an extant turtle and is commonly known as the snapping turtle, which is considered the standard turtle when discussing the phylogeny of turtles. The main modification was the reduction of the plastron bones from 4 now down to 3. And so it's important to understand these stem turtles and the modifications of their shells. And even though the origin of their shells is understood, its purpose still remains questionable. So, most people think that the turtle shell was mainly used for protection, but a lot of evidence is now pointing towards the idea that the origin of the shell was actually used for fossoriality, in other words, for digging. And the protective function of the shells first fails to explain the original purpose of broadening the ribs in stem turtles, such as Unitosaurus and Odontocheles. And so, in these early stem turtles, broadening of the ribs alone would actually have left the head and neck unprotected and vulnerable to predators, as well as the epaxial musculature between the dermis and bone. And it wouldn't be until later that natural selection took its course and Odontocheles would adapt to a partially developed carapace where the neural spines would have helped shield and protect certain muscles, which suggests basically that the shielding came later. So if protection was essential in these stem turtles, the body plan would have been similar to amniotes with overlying osteoderms, such as species and animals like alligators and crocodiles that covers the entire anatomy and wouldn't have locomotion and ventilation effects. And so Unitosaurus actually shed new light, and scientists hypothesized that the broadening of the dorsal ribs was actually to withstand compressive forces as it and other stem turtles burrowed beneath the soil. And through osteological and histological testing, scientists have actually determined that Unitosaurus had the prime anatomy for digging when compared to other extant species that have fossorial behavior. And these skeletal structures include the phalanges and claws, the forelimbs, the neck, skull, and thoracic. And in comparing the fossil record, both Unitosaurus and Odontocheles contain large thickened bones in the forelimbs, and this was used to brace compressive forces. And they also had large claws, which would aid in forelimb digging and sifting. And so Odontocheles was very similar to Unitosaurus. And in these figures, we can look at the fossil record, and we can see that Odontocheles had a short, robust ulna. It also had hands that were larger and more robust than the feet. And so, the studying of the fossil record, scientists were able to provide supporting evidence that points towards the idea that the shell was actually used for digging purposes. But with these modifications to improve fitness and to help with fossoriality, two consequences would arise, namely locomotion and ventilation costs. And speed has been a limitation for turtles for millions of years now, and the early indications of the reduction of locomotion speeds would be the effect of the broadening of the ribs and also the reduction of ribs and vertebrae, specifically to Unitosaurus. And this design would be the basis of an enlargement in thoracic body wall rigidity, which would decrease stride length, resulting in the reduction of general speed. But on the other hand, Milleretta retained a body structure that would use the lateral bending to achieve longer stride lengths and ultimately increase their overall speed. And you can see this in the figure. And so this was a limitation from the beginning, but ventilation became a major obstacle as well. And in the early evolution of Unitosaurus and Odontocheles, broadening and fusion of the ribs and neurospines, costal ventilation actually wouldn't have been possible due to the loss of intercostal muscles. And so these early stem turtles adapted to this drawback and acquired a mechanism to use the transversus abdominis as well as the obliquus abdominis muscles. These muscles previously would help in the stabilization of the rigid trunk, but as the dorsal ribs broadened, the need for these muscles became obsolete, and so instead they became the main muscles used in pulmonary ventilation. And in this figure, we have the lungs, the transversus abdominis, and the obliquus abdominis. So the way that turtles actually breathe now is by using the transversus abdominis and obliquus abdominis muscles, which alternate to produce a pumping pattern to generate inhaling and exhaling breathing cycles. So anatomically, the transversus abdominis lies deep to the obliquus abdominis, where it connects to the inferior side of the carapace and surrounds the posterior division of each lung. And so when the transversus abdominis contracts and flattens, intrapulmonary pressure rises, generating exhalation. And as the agonist muscles contract and compress, the antagonist muscle stretches and becomes concave in shape, where contraction can occur in the opposite direction. So at first, ventilation was a hindering factor, but through evolution and natural selection, ancestral turtles were able to compensate for this early obstacle. And that concludes my presentation. And I hope you enjoyed and learned a lot today concerning the fossil record and the evolutionary history, purpose, and origin of the turtle shell.